Alright, so today I'm gonna be explaining this important paper with the title Structure-Aware Transformer for Graph Representation Learning. This ICML paper in 2022. The transformer architecture has gained growing attention in graph representation learning recently, as it naturally overcomes several limitations of graph neural networks by avoiding their strict structural inductive biases and instead only encoding the graph structures via positional encoding. So we show that the node representation generated by the transformer with positional encoding do not necessarily capture structural similarity between them. So to address this issue, we propose structure-aware transformer, a class of simple and flexible graph transformers built upon a new self-attention mechanism. This new self-attention incorporates structural information into the original self-attention by extracting a subgraph representation rooted at each node before computing the attention. We propose several methods for automatically generating the subgraph representation and show theoretically that the resulting representations are at least as expressive as the subgraph representations. Empirically, our method achieves state-of-the-art performance on 5 graph prediction benchmarks. Our structure-aware framework can leverage any existing GNN to extract the subgraph representation, and we show that it systematically improves performance relative to the base GNN model, successfully combining the advantages of GNNs and transformers. So this is the self-attention, softmax of Q, K transpose, V. The output of self-attention is followed by skip connection, and then we give it to feed forward. So absolute encoding refers to adding or concatenating the position or structure representation of the graph to the input node features before the main transformer model. There are also the kernel smoothing. You can see it as a kernel smoothing. You can see the self-attention as kernel smoothing. So F here is just W value times X. And this one is W query X, W keys X prime. Dot product of them, and then e to the this value. This is the kernel variant of that. So the idea of this paper is here. Self-attention can be rewritten as a kernel smoother. Now, the problem with this kernel smoother is that it cannot filter out nodes that are structurally different from the node of interest when they have the same or similar node features. In order to also incorporate the structural similarity between nodes, we consider a more generalized kernel that additionally accounts for the local substructures around each node. By introducing a set of subgraphs centered at each node, we define our structure-aware attention as this. This S denotes the subgraph in G centered at a node V, U for example, or subgraph centered node V here. So these are a set of subgraphs that are centered at each node. Then we calculate the kernel of them. And it can be any kernel that compares a pair of subgraphs. So it does generate more expressive node representations than the original self-attention. So we will consider the following form of K that already includes a large class of expressive and computationally tractable models. And so our phi is a structure extractor that extracts vector representations of some subgraph centered at U with node features X. This is an overview of SAT layer that uses K subgraph GNN extractor as its structure extractor. The structure extractor generates structure-aware node representations which are used to compute query keys in the transformer. A straightforward way to extract local structural information at node U is to apply any existing GNN model to the input graph with node features X and take the output node representation at U as a subgraph representation at U. A more expressive extractor is to use GNN to directly compute representation of entire K-hop subgraph centered at U rather than just the node representations of U. So if we note this by the K-hop neighborhood of node U, including itself, so we can represent U as follows. Having defined our structure-aware self-attention function, the other components of this structure-aware transformer follow the transformer architecture. The self-attention function is followed by a skip connection, a feed-forward network, and two normalization layers before and after the FFN. In addition, we also include the degree factor. The degree factor in the skip connection. So they did experiments on zinc and other benchmark for graph regression and graph classification tasks. So whenever you see this in any paper, it means higher is better. Or this one, it means lower is better. So the metric for zinc, because it's a regression, is mean absolute error. But the other one, because there are graph classification, this is just accuracy. So for mean absolute error for graph isomorphism network is this point. But you see it is reduced significantly to just this number for K subgraph SAT. And this is the attention visualization of SAT and transformer.